Okay. Let's see. So last time we talked about side effect, structs versus classes, kind of the Microsoft backstory with software licensing. So them selling IBM, well, licensing IBM an OS that they didn't have. Talked about Java and how it's platform independent. Put a note here to talk about the virtual machine model for Java, right? Okay. So let's go this route. So with any of these high-level languages, and this is going to differ from, well, actually, before I even talk about that, have we talked about, let's see. Okay, so I just said a word high-level language. We haven't talked about that. Okay, so let's do this before we talk about the Java VM. There are three kinds of programming languages. I think I mentioned this before. We've had a slide that looks kind of like this before, right? Two different kinds, three different kinds, right? So these are from different directions, looking at programming languages through different lenses. So we have low-level languages. Actually, let's start with this. Let's say machine level, machine language. We have low-level languages, and we have high-level languages. So machine language is zeros and ones. Okay, not for human consumption. So this is not the type of language we want to be writing in. We'd be tapping out zeros and ones and have the two-button keyboard and make all sorts of mistakes and that kind of stuff. Now a low-level language, this guy has a one-to-one relationship with the CPU. I'll talk about what that means here in a second. And a high-level language has a many-to-one relationship with the CPU. Okay? So, in order to understand this, we have to talk about what the CPU is. All right, so based on what you gathered from your 150 or 175 class, what would you say the CPU is? What's the definition of the CPU? Brain of the computer? Okay, fair enough. What does it do? So it's the brain of the computer. Well, that's fine, we can say that, but physically, what does it actually accomplish? What problems does the CPU solve? Go ahead.
Doesn't it do logical and mathematical problem solving?
Okay. How does it accomplish that?
I want to say mostly by comparison.
Okay. So the CPU is kind of a resource, right? And ultimately, it's us as humans at the top of the food chain, I guess, in this whole relationship, that has to dictate to the CPU what it needs to do. And then internally, it somehow knows how to do either math problems or some other things, right? Okay, so, we want to think about the CPU as a resource that, when instructed, can accomplish various tasks. All right. I like to think of the CPU as like a magician that knows a whole bunch of magic tricks. Okay. Each of these magic tricks solves a very tiny problem. When enough magic tricks are performed in the right order, a larger, more identifiable problem is solved. Okay? So maybe the real life example of this is if we're going to pick up a quarter off the floor, it's easy for us to say, I'm just going to pick the quarter up off the floor. But the reality is we kind of bend at the waist, then we bend our knees. We're solving all these little tiny problems. And ultimately, after we've moved our hand and grasped the quarter and picked it back up and then stood up, all these things, at that point we can say we've picked the quarter up off the floor. There was a whole bunch of little magic tricks that we know how to perform that had to happen in order for that to happen, right? Can't pick up the quarter until they've gotten down to the quarters level. So that one had to be done in a certain order and that kind of stuff. So think of the CPU as this kind of thing. So just like as a human being, we kind of have our stock capabilities, right? There's certain, we can bend our elbows, we can turn our hands. So we have all sorts of little go-to moves that we have to solve all of our problems in terms of. And then we have some things that we maybe wish we could do, like flying. Stuff like that, that would be cool. But one of the cool things we're going to see in here through the tool we're going to use is that they can perform stuff we can't do. So we can tell like a snowman to fly up in the air and go and do stuff. So in any case, we always have to solve these problems in terms of our abilities or our micro abilities or these magic tricks, however you want to think about it. Okay. So at the end of the day, the CPU has this big list of magic tricks, of things it knows how to accomplish, and at some point, at some level, we have to explain to that CPU, we have to tell it, do this magic trick, then this magic trick, then this magic trick, and something identifiable has been done. Okay, maybe hello world's on the screen or something like that. All right, so now getting back to these languages here, well, ultimately, that CPU has this mapping table that maps a binary number to some magic trick. So when we're ultimately telling the CPU what to do, we're telling it perform magic trick 18, then magic trick 3, then magic trick 241, and it goes and looks up in its binary table, because even though we're saying magic trick 13, it's converting 13 into binary. Okay, so realistically, we would say something like 13 decimal to binary. So the conversion of this, we take 13 divided by 2. That's 6. 6 times 2 is 12 with a remainder of 1. 6 divided by 2 is 3. 3 times 2 is 6 with a remainder of 0. 3 divided by 2 is 1. 1 times 2 is 2 with a remainder of 1. 1 divided by 2, 0. 2 goes into 1 0 times. 0 times 2 is 0 with a remainder of 1. And we read our answer from bottom up. So this is 1101. That's the binary number 13. All right, so if we were telling at the end of the day what the CPU is going to receive is it's going to say perform magic trick 1101. That's what it's going to say. Okay. Now, we've heard of, just from a trivia perspective, we've heard of things like 16-bit and 32-bit processors and 64-bit processors, right? Those types of things. All right, so if we were dealing with a 64-bit processor, we would actually have 60 zeros laying in front of this because it's able to handle 2 to the 64th unique instructions. That's what a 64-bit processor can do. That doesn't mean that Intel, for example, has actually implemented 2 to the 64th. So 2 to the 64th is a lot of instructions. I rounded down. That doesn't mean they've actually implemented that many instructions, but it's capable of doing that many unique things. All right. So that's what the table would actually look like. It would actually be, a bunch of 64-bit integers, where a 64-bit integer is an integer represented in 64 zeros and ones. A bit is a single 0 or 1. 13 can technically be implemented as a 4-bit number, and so we'll just leave it at that for now. But so we would, if we had a 4-bit processor, we would be able to do things up to 1111, okay, which is the number 15, right? All right, so in any case, is that right? 15, yeah. 16. We have an extra 1 here. That would give us a 2, 13. No, 15. I'm right. I was testing you. You probably passed. I got it like a C minus. Okay. So in any case, this whole conversion stuff isn't really comfortable for human beings to do all the time. We just kind of academically learned how to do it, but we're not really binary creatures, right? We do the whole base 10 thing because of the 10 fingers, 10 toes, and it's easy for us to count that way. But computers like binary. They're digital things, on or off, 0 or 1, true or false. So at the end of the day, the computer is going to speak that language, and that's not a comfortable thing for us. All right, so we're going to steer clear of talking directly to a computer in zeros and ones. Now, we got these low-level languages. This means that we're going to, this is going to be more English-like. So we have actual programming languages. An example of one of these is a language called assembly. Okay, and actually there's assembly language for every single CPU architecture that's ever existed. So there's a lot of different assembly languages. But imagine assembly effectively being a list of English-like instructions that each one maps up to one of those magic tricks the CPU understands. All right, so as an example, rather than saying perform magic trick 13, we might say move AX comma BX. That says move the whatever's in this hardware register into this hardware register. So move some memory from one place to another. That might not solve a problem in and of itself, but in the big scheme of things, it actually solves a real problem. All right, to kind of show you this, I'm going to look at hello world. Let's do assembly, get a Linux out of this. See what this guy looks like. Yeah, that'll work for us. All right, so as an example, let me go one more step out here. All right, so as an example, this would be the assembly language program that ultimately prints hello world to the screen. All right, so just at a glance, we can look at this and say, while it looks complicated, this is something that it would be in a human being's wheelhouse to write. Okay? Not something we want to do all the time, but we could do this. So I'm going to kind of walk through this just so we can kind of understand the pattern and understand how CPUs work. So forget about this stuff up here. Our program begins with where it says start. Okay? And down here at the bottom, we have our data section. So this is where we're going to remember stuff. This is our variables. All right, so we have a couple of variables that we're remembering here, kind of unimportant, but we have a hello world string, and this is how the character array is terminated. So that is what makes it a string. And then we're also remembering the length of that, how long it is in bytes. All right, 2 pieces of information, whatever, we just have access to those things. So now here's the actual magic trick. So this is us talking directly to the CPU. Okay, the first thing we're going to do is we're going to tell the CPU to move into, these are hardware registers. So a hardware register is on the actual CPU, it's a variable built out of hardware. Really, 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 really tiny, really, 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 really fast, and really, really, really expensive memory that lives right on the CPU. Okay, so this is as close as you can get to the CPU, and this is what we'll talk about in here in terms of variables or attributes in the context of the actual tool we're going to use in here. But a variable for us is a name-value pair. The name of this is EDX. It's a physical container, piece of Tupperware that we could throw a value into. So what this line says is move the length of our string into this hardware register. The next line says move the entire message into a different hardware register. Okay, so we're kind of staging things. So moving the length into a hardware register in and of itself doesn't solve an identifiable problem other than we've taken this value and we've kind of thrown it there. That's it. Then the very next line we say we're going to take this value, we're going to throw it over there. That's it. So we've done 2 little moves like that. Okay. Then we're putting into this hardware register, EBX, the value of 1. Okay. And this is this thing called a file descriptor for standard output. So this says, whatever I'm going to do, I've staged something. So I've taken the value 1, I've thrown it right there. The implication of that, kind of where I'm going, is ultimately, since I'm trying to print hello world out to the screen here, I ultimately want to print it to standard output, which is our screen. What do I want to print? I want to print the message. And how long is that message? It's length. Okay, so I've kind of stored those things. I've staged them in a couple of buckets on the CPU. The last thing is I've moved the value 4 into another hardware register, EAX. So I've taken 4, thrown it over there. So I've staged 4 values in these random locations, seemingly. Okay, we had to understand kind of how our CPU works and how this architecture works here in order for us to pull this off, and I'll explain that here in a second. So I've staged 4 values. That number 4 there relates to a system call that's part of the Linux operating system called system write. So that's the magical function that's built into the operating system that is related to the magic trick number 4, let's say. Okay, and that guy expects 3 values. It wants to know, where do you want me to write the stuff? It wants to know, what am I writing? And it wants to know how long what I'm writing is. Okay? And it just so happens I tossed those 3 values into some very specific locations that this guy knows to look in. That makes sense? So this requires some knowledge about how that Intel CPU kind of dances with the operating system. All right, so we had to know that. But in any case, we staged these 4 values, and at that point in time, we're actually going to call the operating system. So call the kernel. That's the actual Linux operating system, not the distribution that we usually think of with all the text editors and stuff. The bottom of the end of the day, we have this little program called the kernel, which is the actual operating system. So this is the piece of software that sits between us, the user, and the actual hardware, the CPU. Okay, now we call the kernel. The kernel knows to first look in this little hardware register and say, okay, well, what is it that you want to do? Well, you want to write something. Great. Well, what does system write say I need to do next? It says I need to go and grab 3 values from places that I hope you put them in the right place, because that's where I'm going to go and look. So it looks in EBX, it looks in ECX, it looks in EDX. Gets the values that it's interested in and ultimately writes it to the screen, because that's what this magical command does right here, and the kernel is what actually pulls it off. Okay? Next thing, so now this has completed a magic trick. Okay, this series of actions, this is equivalent to us picking up that quarter. All right, so we have now displayed Hello World to the screen. Okay, and since this is a simple program, we are now done with our program. So we would like the operating system to, complete the running of this program and exit back to the operating system so we can go and do something else on the computer. So next thing we do, we move into EAX. Now notice that EAX here is the exact same memory location as EAX was here. Exact same memory register. So that kind of hints us in, clues us into this idea that the Linux operating system utilizes this hardware register as the go-to place for what we want to accomplish. It uses the other hardware registers, and there's more than just 4 of them, but it uses those to stage values that the system calls that we're going to call require. All right, so now we're passing in system call number 1 to this register, which relates to system exit on the Linux operating system. And it just so happens that system exit requires 0 parameters to work. Doesn't require any input. It just says, okay, I'm going to die. Program is going to be executed, terminated, whatever. So in any case, so we put that system call in there, and again, we tell the kernel to take over. I've staged all my variables, go, and it will read from the hardware registers and do its thing. All right, that's a Hello World program in Linux. If we were writing that same Hello World program in Java, it would be 1 line of code that says system.out.println hello world. Still a little bit non-Englishy, but a lot better than this, right? So when we look at this low-level language, after we've explained this, gone through this doesn't seem that bad, right? But we can still imagine ourselves as computer scientists, as programmers, that maybe we don't want to spend every day, all day doing this. Okay, this seems like it would get kind of tedious. It's kind of cool, fun, and geeky for 5 minutes. And every now and then, if you had to go down to this level to do something, and I'll explain when that might occur here in a few minutes, but every now and then, if you had to do this, not the end of the world, but probably not going to be great for your average temperament if you're doing this on a day in, day out basis, right? Okay, so low-level languages, kind of flipping back to here, we're going to say that these guys are technically doable by humans, but we like power tools. This is us really talking, directly to the CPU. Remember back at one of our first slides, we talked about the job of our programming languages is to allow us to solve problems in a similar way to how we solve problems in real life. This is not how we solve problems in real life. This is not how we think about solving problems in real life. We talked a few minutes ago about picking up the quarter. If I dropped a quarter on the ground and you went to pick it up, in your mind, you would just say, oh, I'm going to pick up the quarter. You wouldn't necessarily articulate all the little joints you have to bend and things like that to ultimately get down to that quarter, even though you know you're going to end up doing that stuff. Okay? You don't think about it like that. So low-level language would mean you have to think about it like that. High-level languages kind of capture our meaning, the semantics of what we'd like to do in less lines of code at the end of the day. So we have a many-to-one relationship with the CPU. So every one line of code that we write in, actually, I probably should say one-to-many, but I guess it doesn't really matter. Kind of means the same thing as depending on which side you read it from. But every one line of code we write on the CPU, or every one line of code we write in Java or pick your favorite programming language, translates into many instructions on the CPU. So as an example, I just said in Java, system.out.println hello world. Here, we'll go ahead and write that here. System.out.println hello world. In our little example here, translated into all of that. Okay? And that's actually that's not even a good example. Most of our commands in high-level languages translate into far more assembly code than this. I/O, writing something to the screen, I/O operations on our computers are expensive. All right, one of the things we'll do once we actually start writing real syntax, either very late this semester or early on next semester, is kind of a magic trick I'll show you, is this idea that if I wanted to write a computer program that counted from 1 to 1,000,000, and in the end all it did was just display one time the final count. From our perspective, that program would run almost instantly. Wouldn't take any time at all to run. If instead I decided to print out every single time the current count, print out 1, print out 2, print out 3, print out 4, all the way up to 1,000,000, that program all of a sudden takes several minutes to run. Okay, because every single time I want to print something out, I have to stop. I have to interrupt the CPU and say, okay, hold on. We have to go and do a whole bunch of crap to tell our standard output to show something on the screen. So it's a fairly complex process to output something to the screen. That doesn't mean it's not a necessary evil, but just from a problem-solving perspective, the more often we are interrupted and have to report back, the slower things get, just like in real life. If you were solving a problem, let's say you had to take out the trash, and as soon as you went and grabbed the trash can, you had to report back in and say, okay, I have now gained the resource of the trash can. I will now deliver it to its destination. And maybe halfway down the driveway, you check in again, more of a progress report, right? Okay, that would be fairly tedious and certainly would slow the process down, right? Okay, so it's that type of thing. I/O is expensive. Okay, so these are our three kinds of programming languages. Machine, low level, high level. We prefer these guys. We can tolerate these guys, and we're changing professions if we were asked to use that guy. Okay? Now, let's see, we were talking about the Java virtual machine model. All right, which is going to lead me to another one of those. There are multiple kinds of programming language slides. So let me drag this guy down here, just a reordering. So Java is a high-level programming language. So that means every line of code is going to translate into a whole bunch of magic tricks. So we can think of it as a power tool for human beings. All right, so we start off with our Java source code. Okay, let's just say Java source. And our Java source which is going to be our high-level language, ultimately has to be converted, I'll put a couple question marks here for right now, into, we're going to call this as bytecode. That's a low-level language. So we're going to translate our high-level language and explode it out into a bunch of low-level language. Okay? So that system.out.println line of code we might write ultimately needs to be converted to something that looks like this. But instead of us doing that conversion, we're going to have a piece of software that somebody else wrote that's going to do the conversion for us to make our lives easier. Okay? So this tool here is something called a compiler. All right, now having said that, I'm going to go back to the previous slide here, and we're going to say there are two kinds of programming languages. We have interpreted languages, and we have compiled languages. All right, so interpreted languages operate through an interpreter. Compiled languages operate through a piece of software called a compiler. Just like in real life, an interpreted example is, let's say that the president's giving a speech, and a German news station wants to cover this speech. If they used an interpreter, what they would listen to is the president would be speaking the words in English. The interpreter would be hearing those words in English inside of his brain, mapping each word over to the German equivalent and then spitting it out to the audience. So there would be a little bit of a delay, right? Okay? That doesn't mean it's not accurate, but there would be a delay. So we would consider interpreted languages to be relatively slow. Okay? But we didn't need to spend time solving the problem ahead of time. We just solved it on the fly. So we brought a person in who just listens to the English and turns it into German and spits it out. Okay? Interpreted languages work the same way. So whenever we run an interpreted language, we take the source code, we run it through an interpreter, which on the fly turns it into something that the CPU can understand. Okay? We're going to call those relatively slow. I use the phrase relative, the word relatively, because computers are really fast. So from our perspective, we're likely not going to really notice a difference. But there is a difference. Okay, so if we're solving a very, very, very complex problem, that's where a human being might start perceiving the speed difference. All right. Now, a compiled language uses a compiler. We're going to say these guys are relatively fast. And the real life example of that would be the White House provided the speech to the German news station an hour ahead of time. They had one of their people look over it, convert that speech into German before the news telecast. And then in real time, they were able to give that speech in German to their viewers rather than having a little delay interpreting it. Make sense? All right, so that's the compiled. Relatively fast, but required some upfront work before we started doing the whole solving the problem. Okay, but we only had to do that work once. So if we had 4 different German stations all covering the speech, and one translator translated the speech into German and then distributed it to those 4 German stations, that conversion work only had to happen once, and now they can all run it. Whereas if each station was using their own interpreter, now it's extra work, right? Doesn't necessarily mean that one's better or worse than the other, but they do have their own, pros and cons, let's say. All right? So Java is one of these guys. It's a compiled language. And actually, it's also a little bit of one of these guys. And we'll talk about that here in the next few minutes. But in general, if we were to describe what Java is, which is ultimately going to be the language we use in this department, for the reason we're going to talk about here in the next slide. Java is mostly a compiled language with a little bit of an interpreted twist near the end, okay? So, having said that, Java is going to use this thing called a compiler to convert the source code, the Java high-level source code, into a language called bytecode, Java bytecode, which is a low-level language. Okay, so let's just define quickly here what a compiler is. So this is a software program that converts a high-level language into a low-level language. Okay? That's what that tool does. You feed it Java, it spits out bytecode. Okay? So it would turn system.out.println into that wall of assembly code we saw, for example. Something along those lines. Okay, so now let's continue looking at the Java virtual machine model. So we have the Java source code, which runs through a compiler, which then converts it to bytecode. This all happens prior to us actually running this program. Okay? That bytecode then runs through something called the Java virtual machine. Okay, well, what's a virtual machine? Java virtual machine. So here, this is the Java virtual machine is what this guy stands for. This is a computer emulated in software that maps instructions into, well, let's see that. Well, maps instructions into native instructions for the underlying host operating system. So in our practical world, forget about Java for a second. If we're running Windows and we're emulating Linux inside of Windows, whenever we do something inside of our Linux operating system that's being emulated, at the end of the day, that gets translated by the virtual machine into the equivalent instructions for Windows. Because Windows is ultimately the guy who's carrying out those instructions. So if we try to send some information over the internet, for example, even though you're running the Linux operating system, you're running it inside of a virtual machine, which is a piece of software that's ultimately running on Windows. All right, and that virtual machine is going to translate that internet request that came from Linux into something that Windows, the equivalent request that Windows understands, so that Windows can actually perform that request on behalf of the virtual machine. That makes sense? So an extra little step, again, that's kind of the interpreted part. All right, so even though it's compiled, Java, the virtual machine itself, at the very last step, has to convert whatever Java was trying to accomplish, whatever the virtual machine actually wanted to accomplish, into the equivalent for the underlying host operating system, Windows, Linux, Mac, whatever. Okay? So this virtual machine, we could say, from the Java perspective, since this isn't like a full virtual machine from our perspective, like we're not running an operating system inside of an operating system. This is a very limited machine, that is, it only knows the Java world. It only knows how to do Java stuff. All right, and this virtual machine translates Java's idea of doing something into the equivalent already executed version of that on Windows or on Mac or on Linux. All right. So we could actually say here for the Java virtual machine, it would be fair for us to say this. Translates Java bytecode, which is low level, into native assembly on the host OS, which is also low level. So it translates from one low-level language into another low-level language, maintaining the equivalence in terms of, what it's actually going to accomplish. That doesn't mean that doing something using Java on a Mac is equivalent in performance to doing the same thing using Java on a PC. Because it could be the underlying instructions are more or less efficient on one operating system versus another, but you will guarantee that they're equivalent. They'll both pull off the same task, might not be the same speed. All right, so Java source code gets compiled into bytecode, which then runs through the virtual machine, which then turns it into native assembly, which then runs on the CPU. All right, and it's for this reason, let me just make sure I said this at some point, Java is platform independent. All right, so rather than you writing your Java program for Windows and your Java program for Mac and your Java program for Linux, Sun Microsystems, the original makers of Java, was bought out by Oracle several years ago, so now it's Oracle. But they wrote the virtual machine for Windows. They wrote the virtual machine for Mac, wrote the virtual machine for Linux. So they had 3 different versions of the virtual machine, and each of those versions knew how to turn Java bytecode, which is consistent across all the operating systems, into native assembly code for that platform, for Windows, for Mac, for Linux. Make sense? Okay, so this would be kind of the interpreted step right here. This is the compiled step, but most of the work is being done at the compiled level. We can understand if we're going from low-level language to another low-level language, we can do a one-to-one mapping, so that's not as complex of a task, right? All right, so this is how Java is platform independent. It's also why we can say Java is relatively slow. Again, relatively compared to other high-level languages. Okay, and at some point did I start drawing our chart, our picture of evolution of languages? Yep, this guy. So it would be fair to say that Java, from a pure performance perspective, is slower than these two guys. Now, having said that, it does also bring some additional things to the table that maybe makes our life a little easier. We talked about that a little bit last time, and we'll talk more today. But there's trade-offs there. Okay. So that's the Java virtual machine model. All right, and did I introduce evolution of Java somewhere up here? We talked, yeah, here, evolution of Java. So we kind of talked about how it removed the idea of structs, incorrectly assuming that structs and classes are identical, except for the function part of it. But it also took a lot of the stuff, a lot of those decisions away from the programmer. So that's kind of the benefits of Java. So fine, it's a little bit slower, but it's also a little friendlier. You can get into less trouble as a programmer in Java. I think I probably said it's something like an automatic transmission versus a manual transmission last time, something like that. Okay. So now we want to think about C# versus Java. So C# is actually one of Microsoft's languages, but we need to tell a little bit more about Microsoft in order to understand this. So when Java first came out, this was in the very late 90s, let's say. Yeah, 90, actually not that, in 96, 97, something like that, not very late, but the later 90s. And this language wasn't immediately viewed as being slow, because back then, the things we were asking our computers to do weren't the same things we're asking our computers to do today. Okay, because it was a lot more we were asking them to do in late 90s than it was in 1970, but still not where we are today. So computers are a lot faster today. So having said that, we didn't immediately look down at Java and say, well, you're not fast enough for a lot of applications. So for example, you would never see Java being used today to write video games, unless it was like an Angry Birds type thing. Okay, it could probably handle that. But you wouldn't see Battlefield or something like that, Call of Duty, written in Java. It's just not going to be able to keep up, because you really need to write that at a much more native level. You don't want to deal with that interpreted step, because that's going to slow things down. When with video games, we want it to be pure speed. All right, so having said that, let me talk about one thing ahead of time before this Microsoft story. So maybe answering the question of when we would write assembly code today. We talked a few minutes ago about low-level languages certainly seem like they're doable by a human being, but not something we would prefer to do. Can you think of a scenario today when we might have to write some assembly language based on what we've talked about today? From a human perspective, from a computer programming perspective, who is producing a majority of our assembly language today? What tool produces a majority of our assembly language? This guy, right? So we're trying to use high-level languages as often as we possibly can, relying on compilers to produce most of our assembly language, converting our high-level language into assembly language. All right, so the assembly language that's produced is only as good as the quality of assembly language that the compiler can pump out. Now, do you think compilers today are probably better than compilers were 10 years ago? Yeah, we've gotten better at making efficient code. In fact, we might even say one of the jobs of a compiler is to make bad programmers look better at the low level. So as long as you're writing accurate code, that is, code that solves the problem, a compiler might turn your code into more efficient underlying low-level code. Okay, so back to that idea of picking up a quarter. So let's say that I asked each of you to write an algorithm for picking up a quarter. But I said, I want you to write the algorithm based on my approach to picking up a quarter. Okay? And I start picking up this quarter in this really weird way. I do all these weird movements and stuff like that. They're completely unrelated to picking up a quarter. All right? Now, some of you might take me literally and say, okay, well, this is what he asked for, and write crappy low-level code, right? Ultimately, quarter got picked up, but you were bending joints that were not required to pick up that quarter. Now, some of you, so you're the compiler in this, right? Some of you might decide, okay, well, I'm going to optimize Lippmann's approach to picking up that quarter, and we're going to kind of streamline this and get this done in a little bit less funky looking way. So that would be a better compiler, right? All right, so our modern compilers, the hope is they do a better job at doing those things than historical compilers might. Now, having said that, it would certainly be less likely today that we'd have to write any assembly code than it would have been 10 years ago for the same reason. Our compilers are outputting better and better quality stuff. Now, having said that, there are sometimes scenarios where, because of how high-level languages are written, we are forced into doing something a certain way. For instance, we might need to check to make sure that a certain variable has a value in it before we're allowed to use that variable. Okay? Because Java, for example, will scream at us and say, this variable may not have been initialized. Okay, but maybe as a human being, and you're the one who wrote this solution, maybe you know that even though Java is not able to read my mind, I know for a fact this guy will always have a value in it right here. Java won't let me get away with assuming that it will, but I know for a fact it always has a value in it. And maybe that particular part of this problem, maybe you're writing a video game, maybe that one part of the game needs to be really fast. And you might choose to go down into the assembly language level of this and say, I'm going to tweak this and remove some of this extra error checking. Okay, error checking that Java forced me to do, even though because I understand the exact nature of this problem that I'm solving, I know these couple of circumstances, these couple of questions I asked here are not necessary. Okay? Therefore, we're going to remove it from the assembly code, speeding up that aspect of our application. Okay? That would be an example of when we might still need to write assembly code today. Few and far between, but technically possible. Make sense? All right, so back down here to the Microsoft story. So let's say maybe video games when the compiler produces assembly that is too slow. We'll just say whatever that means. All right, so in Microsoft fashion, they decided, let's steal Java. Java came out. It's a pretty good programming language. Back at that time, Microsoft kind of ruled the roost when it came to programming languages. They had a product called Visual Studio, inside of Visual Studio, they supported several languages: Visual Basic, Visual C++, were their big ones, and they were obviously always looking for what's the next latest greatest language. See, a lot of people were lulled into this idea that Java was what was next. Okay, where in many ways Java was what was next, but Java has distinct disadvantages that make it not necessarily the best tool to solve every job today. The reason I mentioned a few minutes ago that we use Java in the department here, as you can see in this evolutionary picture here, Java came from C. This is a pretty direct lineage. So if you know Java, you can backtrack and learn C++ pretty quickly. You're just having to learn that whole memory pointer way of doing things. And then you can also go back and learn C pretty quickly. You just have to make that assumption that objects don't exist. Got to change your problem solving a little bit. But in terms of syntax, these look basically identical. Okay, not a whole lot of syntax differences between these languages. So Java becomes a very good fit there. C#, you could say the same thing. We're kind of getting ready to talk about the C# story here in a minute. But the biggest reason why Java is a good education language is I don't have to worry about what kind of machines you guys have. So you can do your homework on Windows, on Linux, on Mac, on Turkey Baster OS, whatever it is. Okay, so that's where Java fits in education very well. So back to this, Microsoft stole Java. So this is what Microsoft does, and it's fine. All the big companies, they try to get away with whatever they can. Our laws allow big companies to steal something from young guys. I probably used the example last time of, if you're a, 18-year-old and you wrote a piece of software in your underwear in grandma's basement, and Microsoft steals the software from you, and then you sue them outside of court, and they settle with you outside of court and give you $10 million for your software, you're pretty happy, right? Okay, because you probably didn't have the resources to do with that software what Microsoft is ultimately going to be able to do. Every now and then, somebody is onto something special, and they win that lawsuit, and they're not going to take the out of the court settlement from Microsoft. But Microsoft, they'll just pay the fines for those things and move on with life. Okay, but Microsoft's approach to a lot of problems from a time to market perspective is it's easier to steal something and pay the fine or pay off the person than it is to come up with it on our own or compete. And that's okay. I mean, you don't want to demonize them for something that the law allows them to do. It seems unethical. That's different. This is a big business thing, and I don't think we're going to defend them on the ethical side of things. But in any case, Microsoft tried to steal Java. Difference is that the makers of Java, Sun Microsystems, this wasn't some kid in his underwear in grandma's basement. This is a big company. And they decided not to just roll over and play dead, so they fought Microsoft on this. And Microsoft lost. So at that point in time, Microsoft had to go and drop Java from their offering. They couldn't use the language. And that's when they invented C#. All right, I was at a ACM conference at the University of Illinois in Urbana-Champaign somewhere in the early 2000s, 2001 maybe, when this happened. And first of all, you always go to the Microsoft booths at these things because Microsoft gives away the best free stuff. The other guys are giving away bouncy balls and stuff like that. Microsoft is giving away professional version copies of Visual Studio. It's like a $600 piece of software. We had already pirated it, so we already had it. So we went and sold it on eBay. This is when eBay was new too. So keeping along these ethical guidelines. That's why you show up to Microsoft things. But in any case, so we'll start talking about this next time. Microsoft effectively introduced C#, and every feature of it was basically Java, with just a different syntax. But we can say the same thing was true when we say Java to C++ and C++ to C. All right? All right, I'll see everybody on Wednesday.